And we're rolling. All right, so this is problem number 48 out of the 4-7 homework set. Okay, again, I did this key a while ago, so I'm going to have to kind of refresh my memory with the key that I have on the paper here now. Boat leaves the dock at 2 p.m., travels due south at a speed of 20 kilometers per hour. Another boat that has been heading due east at 15 kilometers per hour reaches the same dock at 3 p.m. At what time were the two boats closest together? Okay, so what am I trying to do here? Minimizing distance, right? Because that's what I'm trying to do. I'm trying to find when the boats are closest together. Now, distance formula is easiest when they're coordinates, right? If I'm trying to find when they're the closest together, I know I'm going to minimize distance. I don't know why I always do an exclamation point after. Minimize distance. So d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared, right? This is just a Pythagorean theorem. Right? Difference in the x's squared plus the difference in the y squared.
Can you draw it? Because I think my.
Oh yeah. Don't worry, I'll draw it. But that if I'm doing this problem initially, that's the way I think about it first. I write out what am I trying to minimize or maximize, and I write out that equation. I write out that equation and try to figure out if I can somehow use the context of the problem to fit the distance. All right. So let's say this is at, and this is crucial here, at 2 p.m. Right? This is at 2. I'm going to draw my diagram that it is so that it is at 2 p.m. Okay, let's make the dock D 0, 0. Let's make that our origin. Look at smiling face. So the dock is the origin, and we know boat 1 is moving due south, right? This way. Here's boat 1. I know that it hasn't moved yet. This is at 2 o'clock. It's starting at the dock and then going southward. It's going south at a rate of 20 kilometers per hour. So if I want to think about it in terms of distance, at some point it's going to be the same x value, but the y value, remember that distance is equal to rate times time, right? Yeah, rate times time. Is it divided by time? Rate divided by time? Yeah, 60 miles for 3 hours you're going. No, times. 60 miles per hour for 3. I always screw this up. I always think about this as the wrong way. Distance is equal to rate divided by time. 60 miles per hour, and I'm going for 3 hours. My distance. No, that's not right. That's not right. Yeah, it's speed. Why you guys screw me up? It's time, right? I got that right? Okay. Rate times time. Yeah, speed. Rate, speed, whatever. Okay, so yeah, I have that written down. So now I'm going southward, so I'm going to say that my y value is going in the negative direction, right? So if I'm going 20 kilometers per hour, the distance is going to be equal to the rate times the time. So let's just say that this is going to be negative 20 times the amount of time. T. Right? The location, the distance is equal to 0, comma. I'm not moving any left or right. I'm just going southward at a rate of 20 kilometers per hour. So at whatever time this exists at, wherever I take that moment in time, the distance is going to be negative 20, the rate times the time, t. All right, so the other, boat 2, is starting due east, right? Due east, yep. Boat 2, and is moving this way. Now, at 2 p.m., where is he? Yeah, 15, because look, it took him an hour to get there, right? It took him an hour to get to the dock. So we can say definitively, if he was traveling at 15 kilometers per hour, that he is at a point negative 15 distance, comma, now here's where he's, not comma, excuse me, negative 15. And now if he's moving, he's adding, because he's going to the right, 15 kilometers per hour. I did not mean to close my parenthesis yet. 15 kilometers per hour, because there's his starting value, negative 15, and he's moving in the positive direction, 15 kilometers per hour, so times the time. Now, is he going to go any up or down? Okay. Do I have coordinates that I can plug into my distance formula now? Yeah. That's the difficult part about this problem. Everything that I've done thus far, that's the difficult piece about this. Beyond this, it's algebra and calculus. Right? I've got to plug into the distance formula, then minimize the distance. Okay. Any questions on the setup? Because that's, in my opinion, the hard part about this problem. Yeah.
So are these two boats that are meeting at the same dock at the end, or are they?
They're not converging at the same dock. One is leaving. This guy at 2 p.m. This guy leaves this dock. At 2 p.m. This guy's 15 kilometers away due east.
Okay.
He's traveling toward. Basically, what's happening is at 2 p.m. it's going like this. Okay, and we're finding when they are the closest to each other. So I bet, in my opinion, it's somewhere like right there. You know, because this guy's going to keep moving southward, and this guy's going to keep moving due east.
Thank you.
Yeah. So now, that's like one of these problems. You ever do that?
What?
You ever do that?
Oh, what is this?
Take your two fingers, and then make your right hand circle forward, and your left hand circle backward, and do it at the same time. Oh wait, better the other way. You ever do that? And then you keep going back. So you go back, around, back. Okay. Sorry. Okay. Hold on, we'll track it. Square root of. So let's make boat 1, x1, y1, boat 2, x2, y2. Yeah, that's what I did on my key as well. So this is negative 15 plus 15t minus 0 squared plus y2, boat 2, 0 minus negative 20t squared. It ends up being a plus in here, but it doesn't really matter because I'm going to square it anyway. It'll go positive no matter what. So d is equal to the square root of, now I've got a FOIL this guy here. So 225, negative 15t, negative, I'm going to cheat a little bit, negative 450 t plus 225 t squared. And then plus this additional 400 t squared, because squaring 20t. So d is equal to the square root of, looks like I've got 625 t squared minus 450t plus 225. Now, remember the method that we did yesterday, finding the minimum value of the distance is really the same thing. It occurs at the same minimum value as the square root of the distance. So what I'm going to do is treat this like d squared is equal to 625 t squared minus 450t plus 225. Why can we do that? Because the minimum values are going to exist at the exact same place. Like the minimum of this, I'm going to try to minimize this function. I would find the derivative of this function. but the minimum values of the square root of this is going to occur at the same minimum values of this, the t values, because basically it's going to occur at the same minimum, like the smallest time is going to be equal to the same smallest time of its square root. Okay, I'm not actually looking for the distance, I'm looking for the time that that distance happened. So that's going to occur at the same spot. It really just simplifies things for us. If you'd like to find the derivative using the square root, more power to you. But it will occur at the same spot.
I was wondering, because they, that also did it like that, except for they used the diagram here.
Oh yeah.
And then they didn't take the square root of the t squared, I'm like, why?
Yeah, because it just makes life easier a little bit. That's the way the book does it too, so I'm not surprised. All right, so let's find d squared prime, right? Let's find the derivative of this. So looks like it's 625 times 2, which is 1250. T minus 450. See, it's so much easier to do that rather than finding the derivative with the square root attached to it. I set that equal to 0. So 450, I add it over to the other side, is equal to 1250t. And then I divide by 1250. It looks like it's 0.36. Let me just double check that number. 450 divided by 1250. 0.36, yep. And that's the time. Like, think about the context of the problem. What was it asking me? At what time were the two boats closest together? Well, after 0.36 of an hour. So 0.36 of an hour is 21 minutes. So 21 minutes, and then 0.6 of a minute. 0.6 times 60 is 36 seconds. 21 minutes, 36 seconds. After 21 minutes, 36 seconds. So we could say at 2:21:36. Yeah. I just took 0.36, and that was 0.36 of an hour. So I just multiplied it by 60 to find how many minutes it was. And then I took the 0.6 off, because it was 21 minutes and then 0.6 of a minute. So I multiplied that by seconds, 60 seconds, so 36 seconds. So 21 minutes, 36 seconds. If you really wanted to get picky with it, you could say 2:21:36. That's the exact time that happened. Greg.
So going back to like the when you plugged in the coordinates for the distance, like
Yep.
x2 and x1.
Yep.
Where you just get rid of the 0.
Yeah.
Okay. So
Yeah, because it was. Yeah, it would have been minus 0. Yeah, I don't know why. I didn't write it here, but I wrote it there. I don't know. But it would have just been minus 0, so I left it off, and this is 0 minus that thing.
Would you like, because that's what that just you solve what's inside the parentheses first, or are you still like multiplying both?
I foiled this,
Okay.
and then I just, because this was 0 minus that, I just squared that.
Okay.
Yeah.
So like there's a 0 in there, you can just get rid of this.
Right.
And because of the
Right. Yeah. Well,
Yeah,
are there any other questions about this one? Okay, number 12. Where am I at here? Oh, is this the one where you got to cut out the pieces? I like this problem. You know what's funny? We do this problem in algebra 2, but you probably don't remember it. Do you?
That's my every time I see one like it, I get like
Flashback.
I really do. Same with the boat one. I remember doing something like.
Yeah, there was one problem where like the guy was like rowing upstream versus rowing downstream.
Yeah, but
Current working against him, current working for him. We're actually about to do that in chapter 8.
what we were doing, we were doing like the effects of like a wind
airplane
on a person.
Oh yeah.
And then where the actual.
Yeah.
I totally forgot how to do that.
I know we did it. I just don't know how we did it. So what am I trying to find? Now, I didn't screen capture this part in, but I'm finding the largest volume, right? So I'm going to, I know I didn't screen capture that part in, but I'm going to maximize volume. Now, I really don't know how to create this equation yet because I'm not exactly sure what this is going to look like. I should create my diagram before I create my equation. Consider the following. You guys ever watch Bill Nye? Bill Nye, the science guy? He always said that. Consider the following. You know who I had for 6th grade science? You guys know the Peppers? Like Abby Pepper and Madison Pepper. I had Mr. Pepper. For, yeah, like their dad. I had it for 6th grade. Yeah, he taught it in North Campus. All right, consider the following. A box with an open top is to be constructed from a square piece of cardboard. So I've got a square piece of cardboard with, 3 feet wide. So this is a full distance of 3. Same thing down here. But I am going to cut out a square from each of the 4 corners. So I am going to go, no. And I'm going to call each of those pieces, you know what, let me erase that away so it's a little bit more. So I'm cutting away squares of all equal length. So like this is X, this is X, this is X. I mean, they're all X, whatever. You get the idea. I'm cutting out little squares. So I'm calling all of those X. And I know that, actually, I don't need a second equation here, I don't think. Because think about this. If I am folding this box, like let me create the edge lines here. That's the bottom of the box, isn't it? And I'm folding those pieces that I cut up so that the X's will match. Okay? So volume is really equal to, again, we could write it as length times width times height. But I can create my volume equation just by that diagram. Look at the bottom of the box, the base of the box, what I outlined here. What dimension is that in here? This is 3. The full length is 3. 3 minus x? 3 minus 2x. So this is 3 minus 2x in here. And isn't that 3 minus 2x here as well?
Yes,
I'm not even introducing a y. So I have 3 minus 2x, 3 minus 2x, and then look, what's my height of my box? X. So the volume is 3 minus 2x times 3 minus 2x. Oops, that's a minus. 3 minus 2x minus 3 minus 2x times x. That's my length times width times height. See, in algebra 2, all we did was like create a polynomial to represent the volume. But now we're taking a step even further and saying, okay, what is the biggest volume that we could possibly get with this set of parameters? Well, I've got to find a polynomial so I can find the derivative of it. All right, let's FOIL this. That's 9. My inners are negative 6x. My outers are negative 6x, so minus 12x. My last is a plus 4x squared. And then times x. So my volume is a 9x minus 12x squared plus 4x to the third. So there's my volume. And now I'm going to find the derivative, which would be 9 minus 24x plus 12x squared. And I'm just going to double check. I'm on the same track as my key. Yeah, 9 minus 24x plus 12x squared. Okay, good. So there's my v prime. Now, in my opinion, I could divide out, I could try to factor this, but I don't know. Can we just use quadratic formula? 12x squared minus 24x plus 9. Yeah. No. The opposite of b plus or minus the square root of b squared minus 4ac all over 2a. There we go. Make sure you put parentheses around the negative 24 squared. A lot of my algebra 2 students don't do that. They make it negative. They don't put parentheses in the negative. Come on. Square negative, positive. Negative 24 squared minus 4 times 12 times 9. So inside the parentheses, ooh, look at that, 144. Perfect square. This was factorable. 24 plus or minus, that would have been square root of 144, so 12 over 24. So to find our two solutions, I would say 24 plus 12 over 24. Oh, I should do, oh, stop that. 24 plus 12 divided by 24. So 1.5. Or the other possibility, 24 minus 12 divided by 0.5. So those are the two possibilities where my critical point could exist. So this is a case where I actually have two possibilities. But guess what? What happens when you plug in the volume when x is 1.5? Think about if my x value is truly 1.5. What would the dimensions of the box be? 0. Like, think about cutting out 1.5 from each direction. That would mean that this would be 0. Yeah, so does 1.5 even exist? No. So this got to be 0.5. Now, what was the final answer? What were we looking at to do here? Find the largest volume. So I do have to go ahead and plug it back in. I know x is 0.5, so I'm going to find b of 0.5. So I'll go and just plug it into my volume formula. 9, hold on, I did see your hand there, Greg. Just one second. 9 times 0.5 minus 12 times 0.5 squared plus 4 times 0.5 to the third. Just double check I'm plugging that in right. Biggest volume is 2. 2, what's my unit? 2 b cubed. That's the biggest volume I could possibly have. Greg, a question.
Is there a way that you can, algebraically, that you can solve for like which x value to use?
Yeah, like if you plugged, guess what would happen if you plug in 1.5? It would be 0. It would be 0. Yeah. Because if you went here, look.
Oh, yeah.
You know, plug in 9 times 1.5 minus 12 times 1.5 squared. Yeah. It's a 0, the function, so it's just 0. Yeah. Yeah, any other questions on that one? Yeah.
I did that. I have and then I just have it.
Yep.
So.
Yep. Yeah, you guys are the same answer, right? Yeah.
If you want to
I got one. It's fine, so.
What number did you say, 14? 14. A box with a square base and open top must have a volume of 32,000 cubic centimeters. Find the dimensions of the box to minimize the amount of material. Now, what is actually going to minimize the amount of material? The surface area. The surface area is really the amount of material. So when I go to start this problem, I'm going to say, I'm going to minimize the surface area. That's really what I'm looking to do. Minimize surface area. So now, I'm going to draw this out, and then I'll create my surface area formula. That might help. Okay, I've got a box with an open top. Here's the front face of my box. Okay? So I've got a box with an open top, and it's got a square base. A square base. X by X. Box with a square base and an open top. Oh, yeah, okay, I'm sorry. We don't know the dimension of the height of the box. That's the other piece here that we need to know. Now, I can create an equation of my surface area. My surface area is going to be, now, it's an open top box. So that means I've just got the flat bottom. So x squared plus 4 sides around that are all the same, right? I've got x times y, x times y, x times y, x times y. So 4 of these xy's. I don't know why I did parentheses, but I did. So 4 of those sides around the box and then just the base. If I had closed the top, I would want 2 of my x squares, but since this is an open top, it's just 1 of the x squares. The restriction I have is on the volume. The volume is equal to x times y, right? So x squared y is really equal to 32,000. So what did I do here? I created an equation that I can solve for y pretty easily, so I can plug it back in here and remove y out of my surface area formula. Let's do that. So y is equal to 32,000 over x squared. So meaning my surface area is equal to x squared plus, and then I've got 4 times 32,000, or actually 4 times x times 32,000 over x squared. Now look, I've got an x over an x squared, so that's actually going to cancel a little bit. So my surface area is going to be x squared plus 4 times 32, what's that, 128,000? Yeah, 128,000. Divided by just x now, because my x and my x squared cancel. Am I going to get a common denominator just quite yet? Nope, not yet. Not yet, because I'm going to find the derivative first, and I don't want to create a quotient rule for myself if I don't need one. I can pretty easily find the derivative if I just rewrite this as x squared plus 128,000 times x to the what? -1. And then it's just a polynomial rule rather than a quotient rule. Because the goal is to find the derivative of that. So let's do that. So I've got a 2x, so derivative of the surface area is a 2x minus 128,000 x to the -2nd, which drops down into the denominator. So that's going to be 2x minus 128,000 over x squared. And now I'd like to get common denominators. You don't have to, but it's, I don't know. I think it might be a good idea to. Because really, I'm just trying to set this equal to 0. I guess if I did, do I really even need common denominators? Because if I set this equal to 0, I could just add the 128,000 over. I think that would work. Let's just do that then. 2x minus 128,000 over x squared equals 0, and I add this piece over. So 2x is equal to 128,000 over x squared. Cross multiply, so 2x to the third. We'll just really multiply the x to the third. 128,000. Sorry, my poor handwriting. So x to the third is equal to, look, 64,000. That's a 6. And when I cube root that, I get 40. X equals 40. And then the final answer to the problem was find the dimensions of the box. So looks like I know my base is 40 by 40. Let's figure out what my y value would be then. Well, take a look. The y value is 32,000 divided by x squared. So 32,000 divided by 40 squared is 20. So if the x is 40, the y is 20. So I've got a 40 by 40 by 20 box. Those are the dimensions of the box that gives me the maximum amount. The minimum amount of surface area with that box. Just to kind of show it, I think it would be a good idea to show how to do this whole common denominator piece. Let me screen grab this real quick over here. Bring it to a new page real quick. Because you might have to do that. Might have to do this. In case you need it. Hold on, please. There we go. Because I'm not certain that you can solve the one tomorrow like just adding it over to the other side. So meaning, if I would have to get a common denominator here, I would need to multiply this by x squared. Let me get red. X squared over x squared to get a common denominator. So that would have been a 2x to the third over x squared minus 128,000 over x squared. Common denominator, 2x to the third minus 128,000 over x squared. And then, so that's my true derivative. So the place where the maximum could happen is where this equals 0. And then you're at this, so 2x to the third minus 128,000 equals 0, which eventually leads you to 40. Right?
So,
Go ahead.
why didn't you do the quotient rule?
That was the end of the derivative. I had,
At the end?
right, I had found the derivative and said, okay, let me reduce my derivative a little bit
Okay.
to get it with the common denominator. Aaron?
This is on 13, but, for 13, you're given 1.5 million.
Yeah.
I expanded that,
Yeah, I did too.
okay, so.
I was worried that it was gonna make a difference, but I don't think it does in the end.
Does it?
I don't think so.
I think,
You think it does?
I think,
Oh,
because I got my x to be 0.62,
well then, yes,
and
it
then my
does. It
y
does
to
make a
be
difference.
2.4,
Then
so I
again, it does.
agreed to it.
So I was worried that it was gonna make a difference, so I just left it in.
If we were to do like problems to review from this month, that
I would look at the homework problems, and not just the homework problems, but the ones that are in the homework set that we didn't do as well. That look extremely similar to the ones that we did do.
but there's no like.
Nothing too fancy. You think 12? I've already, wait, where's 12? 12, the ABCD? Cutting the box one. Yeah.
Will we have any ellipses? I don't know what.
Ellipsi? No.
Okay, 'cause I didn't know how to do that.
We only do like perimeter area volume and distance.
This is one.
Wait, what's the surface?
Really, it just kind of depends on the type of the box, right?
Yeah, there's no universal, it's the area of
The side,
whatever side or base.
Figure out what the areas in each side is. That's up there. So, Taylor,
You're simplifying for me.
sure. Hold on a second. Question? Yeah, I was gonna post the homework key, closer to the end of the day today. I'll send out a reminder when I do it. Yeah, a lot of it, I think I'll do it when I find it.
Yeah. Or too long.
You wrote me a long note.
Hello, was it your last time?
I mean, I was hoping to try to get you guys to do most of it so that we can answer my questions.
I was in a turn last night.
Yeah.
English literature?
Yeah.
Wind
is killing me.
Yeah.
It was breeze. Feel, there's a breeze. There's a hair in my neck. Sorry. Sorry. Oh, you fucking sorry.
I'm just trying to simplify.
Sorry.
That's what it is. How do you pull out? How do you pull out?
Yeah.
Isn't that?
No, I mean, it's first time in the
Yeah.
4 o'clock. You don't need to. Well, because you can't get there early for turn. You're trying to distribute it.
You can just.
4 o'clock.
Yeah.
We do so many complicated things.
No, that's what, that's the stuff that gets me. You're like, I'll sit here for.
We just divide by 4.
It's 4xy. Divide by 4x. Mind blown, man. Mind blown. All right, we'll take our quiz tomorrow. So long, everybody watching at home.
Everyone knows how to